Okay, so for the following circuit, we have to find IT and Vt for all times, and we're told the unit step function u minus t is 1 when t is less than 0, and it's 0 when t is greater than 0. So for when t is less than 0, we know that u minus t is 1. So let's write the circuit when t is less than 0. So this one will be 20 volts, 5 ohms here. Okay, and then there's a 0.2 farad capacitor. And then we're told the switch is open, so the rest of the circuit we can practically ignore. To find the current passing through this capacitor, it's equal to the capacitor times the change of voltage over the change in time. And we're going to make the assumption the switch has been open for a very long time. So this is infinite. So I will be 0. So we can pretty much replace this with an open wire. And even if the current is 0, there is still a voltage. So the voltage here will be the same as the voltage here. And again, since the current is 0, the current passing through this entire this entire circuit is 0. This resistor is useless. So for when t is less than 0, voltage will be 20 volts, and the current will be 0. So now let's focus to when t is equal to 0. So when t is equal to 0, the circuit looks like this. The switch is closed. So we can listen to the rest of the part. We can include the rest of the circuit. This is 10 ohms, 0.2 farads, and then there's a current passing through here. So when t is 0, well, what's the voltage going to be? The voltage will also be 20 volts, because when t was less than 0, it was 20 volts. Now the second t is 0, the voltage here can't change instantaneously. Okay, so the voltage will be 0 when t is 0. But the current, we don't actually know what the current value is when t is 0. The reason is because this current is not passing through a conductor or resistor. So the idea of it changing instantaneously doesn't apply here. It passes through a wire. So we don't know what I will be. So now let's focus on when when t is greater than 0. So let's find the current passing through here. It's equal to the capacitance times the change in voltage over the change in time. Time goes to infinity. So we can replace this with an open wire. And so now we have to find the voltage here. So to find the voltage here will be the same as the voltage here. Oh yeah, and the unit function when t is greater than 0, the unit step function is equal to 0. So that means this voltage source we can just ignore and replace it with a closed wire here. Okay, so now let's redraw the circuit. Here, let me draw it like this. There. So we know the voltage here will be the same as the voltage of this entire region. So let's call this V. Also, we know there's a current passing through here called I. And this is 5 ohms, this is 10 ohms, and there's 3 amp current passing through here. Let's do a nodal analysis. Let's call a current passing through here I1. So the node for V will be I1 plus 3, which is entering it, is equal to I1, which is leaving it. So I1, it goes from 0, the ground node, to V, so 0 minus V, all over 5, plus 3 equals I1, which is V over 10. So let's solve for V. So it'll be 3 equals V over 10, and bring the minus V over 5 to the other side, so it'll be V over 10 plus 1 over, plus V over 5, which is 0.3 V, and that makes V to be 10. Okay, but this V equaling 10, that's not what that's not the voltage for when t is greater than 0, because the voltage is going to be changing as you increase the time. So this v will be v infinite. Okay, all right. And so to solve for what vt will be, well, we have to know what kind of circuit we're working on. So we see when the switch was closed. We see when the switch was closed, there was this source here, and when it was open, there was this source here. So we will have to use the following formula. Vt will be equal to v infinite plus v0 minus v infinite times e to the power of t over the time constant. So the time constant will be equal to the resistance equivalent between the capacitance terminals times the capacitor. Capacitor is 0.2 fards. I'll just remove the f. Okay, and the resistance equivalent will be pretty much between this terminal. So to find the resistance equivalent, we're going to turn off all sources, independent sources. So this is just an open wire here, and we can just ignore it. And these two are in parallel because they share both the same node. So it'll be 1 over 5 plus 1 over 10 to the power of minus 1. So the resistance equivalent is 3.333 times 0.2, or just 1 over 3 times 0.2. So our time constant will be 2 over 3 seconds. Okay? And now let's solve for Vt. So Vt will be equal to V infinite, which is 10, plus V0, which was 20, minus V infinite, which is 10, times e to the power of t over the time constant, which was 2 over 3, which 1 over that is 3 over 2. And then 20 minus 10, that's just 10. E to the power of minus 2 over 3 t. Now we need to solve for I of t. And I of t is actually going to be really easy. So recall, so I is just this value, right? I will be equal to 0 minus v over 5. So I of t will be 0 minus v of t over 5. So we'll just have to divide this by negative 5. So it'll be negative 2 plus 2 e to the power of minus 2 over 3 t amps, and this is in volts. And there we go.